part of vacuum polarization that's reasonably transparent in Weinberg. The rest of his treatment of that is subtler, and I may do some of that next week, but I don't think I'm going to do it today. So let me just go back and remind you of some things about spinors. And first of all, particles. So P plus or minus a half, and this represents a particle of momentum P, spin plus or minus a half, and kind. So this is the kind of particle or type of particle. And in particular, this is an eigenstate of, it's an eigenstate of angular momentum if the momentum is in the z direction. And, or equivalently, I'm going to switch to S. So it's an eigenstate of Jz if the momentum's in the z direction. In general, the creation operator A of P dagger S and N takes the vacuum to this state P S N, and in particular, if the same creation operator takes a state P1 S1 N1 P2 S2 N2 dot 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 into a state P S N, and then P1 S1 N1 dot dot dot. So that's what the creation operator does. And for antiparticles, these equations are just the same thing with n replaced by n sub c. So n is kind, n sub c is antiparticle of kind n. Well, in other words, if n is electron, n sub c is positron. And these are then pz hat. S n sub c is s pz hat s n sub c e to the, well, let's see, I skipped an equation, I think. Yeah, I skipped an equation here. In between these two equations, I wanted to write down e to the minus I theta jz on the state p z hat Sn. So this is a state of momentum in the z direction, rotation about the z axis. This is e to the minus I theta s pz hat Sn. So because the state's an eigenstate of Jz, this is Jz. Because it's an eigenstate of Jz, e to the minus I theta Jz acting on it is e to the minus I theta S on the state. And for the antiparticles, the similar equations are e to the minus I theta Jz, pz hat S, and c is e to the minus I theta S, pz hat S, and c. And of course, a dagger of P, S, and C on, say, well, any state, I'll just write it this way, is P, S, and C, semicolon, and whatever else is written. Okay. Now, how do these states transform under general rotation? Well, a unitary operator representing a rotation about the axis theta of angle length of theta, a dagger P S n U inverse or U adjoint well, let's not use too many blackboards at once. E to the minus I theta dot j a dagger P S n e to the I theta dot j. So this j is the angular momentum operator. It's a vector, and then this gives us d of r of theta, s prime, a dagger of r of theta on the vector p. So I don't know quite where to put the arrow there. Sn. So the creation operator behaves this way under the unitary transformation that represents a rotation. This is the 2 by 2 rotation matrix, and that is.
Should there be an S prime in the A dagger? Are you summing over S prime?
Thank you. Yeah, there's a typo there. Some more supplies for your candy store. No, you get 2 for a correction, 1 for a question. Now, what is this D? Oh, is anybody, are you starving? Are you hungry?
He's good.
What is this D? Well, D of R of theta, S prime, this is a 2 by 2 matrix. The 2 by 2 matrix is e to the minus I theta dot sigma over 2, where these are the Pauli matrices, and it's just the SS prime matrix element of that combination. And I didn't latex this part, but I believe from memory this is cosine theta over 2 minus I theta dot sigma sine theta over 2, and this is the 2 by 2 identity matrix I. So that's what that 2 by 2 matrix is. It's the thing that you are surprised about when you learn about it in quantum mechanics. And you think of it perhaps the first time you see it as something horrible. And then after a while you start to think of it as one of the simple equations that you're thankful for. You wish all the others were this simple. Now, in particular, if the momentum of the state P is in the z direction, then it's unchanged by a rotation about the z-axis. And so these equations become simpler in that case. And then what we have is u of r about the z-axis. A dagger, and I see I have some typos here, so this should be pz hat Sn. U inverse or U adjoint R of z theta. And let me again use this part of the board. E to the minus I theta jz a dagger let's see, now I'm a little puzzled as to which equation I'm using here. Okay, I was actually trying to do something more complicated than I thought. So here the notes were right and the brain was wrong. So we're letting momentum be in an arbitrary direction, but we're rotating about the z-axis. And so this is r of z and theta acting on p, comma Sn. Wait, sorry, even that's wrong. God. So if we're just copying this down, this is just p Sn, and this is e to the I theta jz. And so this is then e to the minus I theta s times a dagger of r of theta z acting on p Sn. So this is the creation operator has momentum in an arbitrary direction, but we're rotating around the z-axis. The s part is an this is an eigenstate of the s part is an eigenstate of jz. Or to put it differently, let's look back at this equation. This says how things work for a general rotation. So for a general rotation, what happens is that instead of this, what you have is this 2 by 2 matrix multiplying this. But in the case of the z rotation, it's diagonal. And consequently, if we have spin s, then we stay with s, and s prime has to be s, and we just get this phase factor. So is everybody copacetic with this, or should I explain it again? Okay, so let me get my pen so that I can correct any typos here. Right. So it's the fact that this 2 by 2 matrix is diagonal here. And notice that when we go to a Dirac field, where a Dirac field, of course, transforms as a reducible representation of the Lorentz group, but these two representations of these two by 2 representations of the Lorentz group are the same for rotations. They just differ for boosts, and I'm going to stay with rotations today. Let's take the adjoint of this equation. So that gives us u of rz theta, a of p vector s n, u adjoint of r of z and theta. And what we see then is that that is e to the I s theta, a of r of theta z on p s n. So what we notice here is that creation operators under a z rotation go as e to the minus I theta s. Annihilation operators go as e to the I theta s. And that's because one represents, well, because one is the adjoint of the other. So there's a phase change under Hermitian conjugation. Now, a Dirac field, of course, psi sub a, say, of x is the sum on s integral dqp over 2 pi to the 3/2. And now we have u sub a of P and S, and I don't think we need a kind label for spinors. Well, actually one does, but so let's, all right, I'll put in a kind label, just to be kind. E to the I px, A of P S n, and then I'll write this as plus V sub A of P S n sub C, really, a dagger of P S n sub C, or one could write this as A sub C. Anyway, this is the, for example, the annihilation operator for electrons. This is the creation operator for positrons. So, for example, so that's what we're talking about. And questions? All right, under a rotation here, and about the z-axis. So this is e to the minus I theta jz sine A of x e to the I theta jz. And so this is a sum over S integral dqp to pi to the 3/2. And now, these things remain invariant, but of course the annihilation operators are going to change. They're going to change according to these equations. And so we have here UA of PSN e to the I px e to the minus I theta jz A of PS n e to the I theta jz, and then V sub A of PS and n sub C e to the minus I theta jz, a dagger of PS n sub C e to the I theta jz, and then a bracket, closing bracket. Now, what we're dealing with here is this equation, and so the momentum gets rotated, but because it's a rotation about the z-axis, the creation operator gets this phase, and the annihilation operator gets that phase, and this is a comma, not a prime on anything. Yes?
Are you missing an e to the minus I px on all of your antiparticle terms of the field?
Right. Thank you. I believe those are in the notes. Yeah, they are in the notes. In these okay, so we know how these things transform, namely, what we have then is that this is equal to some S integral dqp 2 pi to the 3/2 UA of PS n e to the I px e to the I s theta A of R maybe I'll just write it as R of theta z P S N plus VA of P S N C e to the minus I Px e to the minus I S theta a dagger of R theta Z P S and C. Okay, so that's how the field transforms due to the action of the unitary transformation on the creation and annihilation operators. Those properties in turn follow from how particles transform under Lorentz transformations and how states transform. By the way, what I should have said at the very beginning is that I'm talking about how we need to construct the spinors U and V. And the point is that the spinors U and V have one role in life. Their role is to allow the field to transform properly under Lorentz transformations. So the field has to transform under Lorentz transformations in a way that's well, I've specialized here to such a simple case that it's not right. I'm about to say, in fact, what that case is. So let me say how it goes. So under a rotation, in fact, under a rotation about the z-axis, psi a of, let us say, x0 and x vector, e to the minus I theta jz, no, that's a plus, is d of R inverse of theta z, AB psi b of x0 and R theta z on x. So the space gets rotated by the rotation. This, though, is an inverse rotation, and this d of R inverse of a rotation about the z-axis is e to the I theta sigma 3 over 2, 0, 0, e to the I theta sigma 3 over 2. So that's a 4x4 matrix, and in particular it's completely diagonal. It's equal to e to the I theta over 2, 0, 0, e to the minus I theta over 2, 0, 0, 0, 0, 0, 0, 0, 0, and then down here, e to the I theta over 2, 0, 0, e to the minus I theta over 2. So that's what that rotation matrix is. It's first of all reducible, and but for rotations, the two 2x2 representations of the rotation group are, well, it's the same representation.
I have a question.
Yeah.
Sorry, to go all the way back to the beginning. So then did you mean to write just an ordinary p vector here on these equations?
Where?
The first two equations that you wrote.
This equation.
Yeah, you wrote like pz hat, but I'm trying to like reconcile how we can get this, like why these equations would be consistent with the equation that we've written over here for how a dagger transforms under z rotations, right? And I feel, shouldn't that just be a normal p if the two equations agree with one another? Because you could just change.
Well, here's the deal.
A on the back?
Yeah, because that P is arbitrary
Here's the deal.
in the field. It's,
Yeah, yeah.
It's an arbitrary momentum in the
Yeah.
Okay, so great question. Let me give you a candy for your store.
Okay. Awesome.
You see, I wanted to say that this state was an eigenstate of angular momentum. And that's true if P is in the z direction. If P is not in the z direction, it's not an eigenstate of angular momentum. Because if your momentum is this way and you rotate about the z-axis, then you turn it into that, you see.
Oh, I see. Yeah, that was my issue, is I was forgetting about the fact that you have to rotate there. And that's why. Because if P is already in the z direction, this rotation on P in your A dagger does nothing.
Right.
And so that's why that state is an eigenstate. Okay. I see. Sorry. Sorry.
No, that's great. In fact, in my notes, in the first version of this, I was sloppy about just this point.
Okay.
I mixed the two up, and
Yeah.
it's there's just a lot of details. Okay, so once again, if we're talking about rotations about the z-axis, then what does this turn into? This thing turns, since this 4x4 matrix is diagonal, this thing turns into the following. It's e to the I theta over 2 psi A of x0, and then r of theta z x, or A equal to 1 or 3, and it's e to the minus I theta over 2 psi A of x0 r of theta z x, for A equal to 2 or 4. Okay, so in other words, we do the rotation on the 8th component, and we see that it gets multiplied by e to the I theta over 2 if A is 1 or 3, but by e to the minus I theta over 2 if A is 2 or 4. And so we have these equations. And now what we want to do is we want to compare this second equation with this earlier well, now I see in my notes I've got the wrong equation label. Yeah, I should have called it, it should be 14. So we want to compare that with God, I hope I wrote this one down. Hold on a second. So it's so did I write down the equation after that? Yes, okay. Right, okay. So now we want to compare this one with this one. So this is the one we want to compare. And so now what do we see? What we see is that for the U spinors, there's no problem. For the V spinors, things are a little bit bizarre. So let's look by comparing these two equations, namely the effect on the Dirac field of the rotation is you multiply the annihilation operator of spin z component s by the I s theta and the creation operator by e to the minus I s theta. So what we've got is sum on s prime e to the I theta dot sigma over 2. I don't know why I did that so elaborately. Because I'm just doing z rotation, so I see I could have written this more simply. All right, let's go to, we'll make it 0 to make things a little bit simpler so we don't have to screw around with now, I really don't know why I did this. This is sort of overkill. We're just talking about rotations about the z-axis here. So maybe I'll just have to forget the notes and just try to do it live here. So the overall factor for a equal to 1 or 3 is e to the I theta over 2. Over here, what we see is that we're going to have UA of PSN. In fact, let's look at just the z component of these things. Just remarkable how complicated this gets so very, very quickly. So if we just look, let's look at ones that are going in the z direction, just to make things simple. So this is PZ hat SN e to the IS theta and right, okay, so the annihilation operator, and if the annihilation operator, if the momentum's the z direction, then this has no effect, and so I don't need to write that part down. On the other hand, over here, we see it's just e to the I theta over 2. So this is UA PZ hat SN e to the I theta over 2. So what this is saying here is that the U spinors have to satisfy this equation for arbitrary S, but there's no S here. So this works. In other words, if for S equal to, this only works for S equals plus a half. And in fact, S equals plus a half then means that UA of PZ hat S PZ hat 1/2 N, so spin up, in other words, has to be something, some arbitrary number, let's call it alpha 0, beta 0. In other words, it can be, we have to get a plus sign here, and so for the plus a half, this thing works, and this only is true for A equal to 1 or 3, right? Plus a half only works for 1 and 3. So here for a equal to 1 or 3, we have the plus, and that means that the spin up spinner has to look like that. On the other hand, UA of PZ hat minus a half N has to be something like this: 0 gamma, 0 delta. And the deal here is, because if S is minus a half, we have a minus a half here, but this equation, in other words, the other equation is, or this equation is, that for a equal to 2 or 4, you get minus I theta over 2. And so that tells us that this is the way the spinors have to be structured. Now, and this is what, of course, everybody believes this. What's subtle is how this works for the V spinors. And for V spinors, you see what we get is we have their VA of, let us put this in the Z direction. This thing gets multiplied by e to the minus I theta, or I S theta. And if it's in the Z direction, there's no change. And on the other hand, what we know is that this is going to be e to the I theta over 2, an overall phase factor VA of PZ hat SNC for A equal to 1 or 3, and it's going to be e to the minus I theta over 2 VA PZ hat SNC for A equal to 2 or 4. Okay, so how is this going to work? It's that if we have VA of PZ hat 1/2 NC, then we want a plus a half, and let's see, did I just screw this up? Minus I theta of 2, 4. Right, okay. So for 1, 3, you see we have here a minus sign. We have here a plus sign. So this has to be 0 for A equal to 1 or 3. So it has to be of the form 0 gamma. Wait, do I have this right?
Do you want to, should have an anti-symmetry, so do you have the 2, 4, 1, and 3 right on the side, your conditions to your right? So you see you're doing 0 gamma, 0 delta for the 1 and 3 instead, where last time the 1 and 3 had the zeros in the second and fourth component?
I'm sure you're right, but I'm not following what you're saying.
These here, what if these are just switched? The 2 and 4 0.
No, I don't think
No, that's okay. Never
yeah,
mind.
I think this.
Ignore what the fuck is.
So well, here, maybe I just shouldn't skip steps here. So if we put S equal to 1/2, this is e to the minus I theta over 2, and what does that tell us? That tells us that this only works. This only works for A equal to 2 or 4. So that means that this spinor for plus a half has to look like this. Okay. On the other hand, VA of PZ hat minus a half NC is going to come in with a plus sign. And you only get that for A equal to 1, 3. So that means that for minus a half, this spinner has to look like this. It has to be Z prime 0, W prime 0. In other words, it has to be just 1, 3. So in other words, the rules for the spinners in the Z direction are opposite for the V's. The V's and the U's have opposite Z component spinners, and in general they have basically opposite spinners. So if we go to momentum 0, then we have U0, for example, a half. Weinberg's choice is 1, 0, 1, 0. U of 0 minus a half, 1 over root 2, 0, 1, 0, 1. And everybody agrees that these are the right choices. On the other hand, now I see that this is a long, detailed, in my notes, explanation. Well, I sort of short-circuited it. All right, V0, 1 half is, it has to be basically of this form, 0, 1, 0, and then, of course, it has to be orthogonal to this one, so we use a minus 1 half, and V of momentum 0 minus 1 half, then 1 over root 2 minus 1, 0, 1, 0. Again, the minus sign comes in because you want to be orthogonal to that one. So that's, I put the notes online. There are a couple of typos. I'll try to fix the typos in the next day or two and put them online in a more accurate way.
Is this what you sent to that guy? Is this what you sent to that guy who wrote that book on quantum field theory? Who got the spinners wrong?
The Schwartz, right?
Yeah.
Schwartz.
Yeah, all right, this is going out to the internet, so let's not talk. Well, as you can see, it's very easy to get confused about this, and in fact, Peskin and Schroeder, I said they get these right, but it's on page 803 and 804, and it's in an appendix, and they just basically say, and surprisingly, and don't give any derivation. Weinberg, of course, gives an incredibly general derivation which works for arbitrary mass, arbitrary spin, but of course as a result it's much harder to understand. I put this demonstration together to make it as simple as possible, but I see that even putting it as simple as possible and working it out myself, I got confused on the blackboard writing it down. There are just so many symbols and equations. But it's really a very simple idea. It's that the U spinners in a field multiply annihilation operators. The annihilation operators transform one way. The V spinners multiply creation operators. The creation operators transform differently. The field transforms one way under Lorentz transformation, namely it gets multiplied by an overall 4x4 matrix, which however is reducible, but for the case of rotations, it's the same 2x2 matrix in both places.
Seems to make, I guess intuitively though, that makes good sense. I said intuitively that makes good sense that it would come out like this, or this form, right? Because it should produce some kind of anti-symmetry in the field. At least in terms of the particle and antiparticle. One of them should create one way, and then the other should annihilate anti-symmetrically the other way.
Well, I mean, I'm more power to you if you can see it that way. I
guess
don't
I see
know,
that it works. I believe you is my point.
All right, yeah.
I believe what you said.
So, let's see, all right, I think I'll just work through some stuff that I did work through on sort of the back end of vacuum polarization. As I said, Weinberg's analysis of this gets very, very subtle, and so I'll just go through some of it here. Pi, and it's actually pi of q squared. The final result that we got to on Monday was an integral 0 to 1 dx of x 1 minus x times a log of 1 plus x 1 minus x q squared over m squared. So that's the formula, and what Weinberg does then is consider the scattering of two particles that, well, one diagram is P1 prime, a photon goes across, P2 prime, and then another diagram here is the one we just computed. In fact, I think I drew the diagram wrong. Let me just see. How did I draw it? Yeah, I had the arrows this way, although it doesn't really obviously make any difference. Okay, so we have to add these two amplitudes, and I thought it would be good to just give you a sketch of it. Let's call Q P1 minus P1 prime. So Q is the momentum going across here, which is what we called it when we did this computation. And there's a delta function of momentum, so if it's Q here, it's Q there. And so this Q is equal to P1 minus P1 prime. It's also P2 prime minus P2. And so the idea is that Q plus P2 is P2 prime. And so the amplitude for this is, and I'm sort of, we're imagining that these are charges E1, E2 over 4 pi squared. There's a delta fourth of P1 plus P2 minus P1 prime minus P2 prime, so total full momentum conservation. And then what's left here is U bar 1 prime gamma A U1, U bar prime gamma B U2, and then the photon propagator in this diagram just gives you eta AB over Q squared, and here it gives you Q squared eta AB minus QA QB over Q squared squared. Okay, so that's the expression, and so you might wonder, where did these things come from, these extra spinors? Well, these are just the spinors that multiply the fermion field, namely these are these U spinors here. So in other words, if we just look at this first diagram, this diagram to lowest order, it's something like P1 prime, P2 prime, 1 over 2 factorial, integral d4 of x, d4 of y, psi bar, let us say gamma A psi, psi bar gamma B psi, A sub A sub B, this is at y, this is at x, and these are at x, x, y, y, and well, the time ordering, I'll put the time ordering here. D4 of x, D4 of y, P1, P2. So this is what Feynman represents by this diagram. And of course, if you follow Feynman's rules as he wrote them or as Weinberg stated them, you can go directly from this diagram to this answer, and from this diagram, well, you can't go from this diagram to this, but if you accept what we did on Monday, you can. Yeah?
Yeah, I was going to say, so U prime means evaluated at like the primed
Momentum.
momenta.
Yeah.
Okay, and then the bar still means you multiply it by beta on the right?
Right. Let me just say that over here. Maybe you could swing the camera, follow the camera. U bar is U dagger beta, which is U dagger I gamma 0. And beta is 0,110. Again, I'm pulling this out of memory as opposed to out of my
And this
notes.
correction term, is this the correction term that we got from computing the diagram and doing all the dimensional regularization, or is this what you get whenever you do that thing that you were talking about yesterday, where you can like compute the sum of all possible like 1 loop, 2 loop, 3 loop corrections to the propagator?
Oh, this is just a simple way.
That's just with one of them.
Yeah.
Okay.
You know, let me tell you something funny. I nearly gave you one of your own.
Oh yeah, you can do that.
So I guess
that was
at this
my
point, it's
file.
going to have to start going the other way. You're going to have to start asking me questions again.
Yeah. Throw 'em right at you.
Okay, so what happens here is that this field creates a photon, which is then absorbed by that one. We also have to say, well, what fields destroy these or absorb these two incoming particles? And you have the choice. You can have the field psi of x absorb P1 and psi of y absorb P2, or the reverse. So that's a factor of 2. And actually you get another factor of 2 when you consider those two going the other way. Anyway, what's left over though, when say psi of x annihilates that, what's left over is a u of let us say P1, and I left out the spin index S, let's say, and then an e to the I px. That's what's left over from this one absorbing that. And from this one absorbing that other one, we would have u of P2, e to the I py. So we'd have these factors left over. And then for creating these guys, we'd have the creation operator, and so those would be a u bar. Well, you see there's a u bar here because of this beta, so it's a dagger with a beta. Anyway, so it's a u bar of P1 prime, S1 prime, e to the minus I, P1 prime, and if we're doing it at x, then that's x, and u bar of P2 prime, S2 prime, e to the minus I, P2 prime, y. So, then you integrate d4th x, d4th y, and you get an overall delta function. And that gives you the first term with these u bars, u bar gamma A, u bar gamma B, and the gammas are over here, gamma A, gamma B. So that's where basically that comes from. Then on the other hand, the higher order diagram is P1 prime, P2 prime, 1 over 4 factorial integral d4th x, d4th y, I guess d4th z, d4th w, time-ordered product of, in fact, let's just write it as psi bar a slash psi at x, psi bar a slash psi at y, psi bar a slash psi at z, psi bar a slash psi at w. So this time-ordered product, and then P1, P2, right, okay. And so now, once again, you have, you might choose that, you choose two of the fermion, two of the psi's to absorb the incoming particles, two of the psi bars to create the outgoing particles, and what's left, and you then have, so basically you have one vertex here, which you might call, you might call this the X vertex if you want to. So you could use all these fields. You could use psi X to absorb the incoming, one incoming electron. Psi bar at X you could use to create the outgoing electron. And then A would create this photon going across of momentum Q. And then over here, you've got P2 prime, P1 prime, and you could choose, say, to have all the W guys deal with that. Namely, so, all right, so I've got everything sort of backwards here. I chose X to deal with the absorption. Let's choose W to deal with the creation of these guys. And, oh hell, now I did it wrong. So I'm doing X to do one, I'm doing X to do absorbing one and creating the other. So that's what I'm doing for X. And then for W, I'm absorbing the other one and creating this guy. Okay. So, and then this A then creates this photon, which then is absorbed by one of these guys and absorbed by one of those guys. And then the fermion loop looks like that. And so we have this thing that we computed earlier. Okay, so that's how that works. And of course, if you follow the Feynman rules carefully and rigorously, you can bypass all this thinking and just write down the answer. And people who work in the field just do that, or they just dial a computer program. But on the other hand, it's useful to work through it with your fingers sometimes. Yeah?
Yeah, so it's kind of a related simple question. Why does psi bar always show up in the QED Lagrangian? Why can't we just use psi dagger? Why do we need the beta?
Okay, good question. Very good question, and let me try to think of what the best way of thinking about it is. I think the best way to think about it is you want the structure to be Lorentz invariant. And if you look at my chapter on group theory and on the 2x2 representation, Lorentz group, and then the Dirac representation, what you've got, you see, is this. You've got, so to speak, psi left dagger, psi right dagger, 0, 1, 1, 0, and then you've got some gamma A, and then you have psi left, psi right. And so what do we have here? Well, this structure here is Lorentz invariant. In that this goes as a 4-vector and this goes as a 4-vector. The part that's Lorentz invariant is L dagger psi right and psi right dagger psi left. And you see the beta does that for you. And so then, let's just sort of remember why it is that this works. And the reason is that D, say, left is E to the I Z dot sigma. I'm talking about a general Lorentz transformation.
Okay.
Boost and rotation. And I'm not saying how Z corresponds to boost and rotation. It's basically the real part of Z is the rotation, the imaginary part of Z is the boost. But D right, if D left is that, D right is e to the minus I Z dot sigma. Z is 3 complex numbers. Okay, so now why does this work? Well, this thing prime is equal to e to the minus I Z dot sigma psi right, and this is psi left dagger, so that's psi left dagger e to the minus I Z dot sigma, and then you see these 2 exponentials cancel. So that's why this works, and correspondingly a mass term, an ordinary Dirac mass term, is m psi bar psi. So it's just m times psi dagger left psi right plus psi right dagger psi left, and both of these guys are Lorentz invariant, and m, of course, is just a number. So that's why this thing works that way. Good question. Did you get a candy for your question?
Yeah,
You did?
yeah.
So I guess, well, you said that, I guess you talked about it, I don't recall, but in the chapter in your book on group theory,
Yeah.
I guess this has something to do with, you wouldn't be able to keep Lorentz, with his question, you wouldn't keep Lorentz covariance or Lorentz invariance in the SU2 by SU, is it SU2 by SU3 for the group that we're talking about here, or which actual group is it?
Well, this is the Lorentz group.
Right, is that,
And-
remind me which one, is that SU2 by SU3, or SU2? One of them, or SU3 is the Poincare group, isn't it?
No. Look, it's a long story.
I'll just read the book,
Do you have a copy?
Yeah, of course.
All right.
3.
It-
They're all around.
All right. So,
One in each office.
yeah, it's kind of a long story, but it's not that long.
Right, there's a
I mean,
There's
it
simple sentence that explains it.
just, I think in the book, I think I put it about as simply as I can, but I can't reconstruct it immediately. So let me continue this story a little bit, because there are aspects to it that are that come up a lot in physics. when we were talking last semester about Dirac fields, Dirac equations, and so forth, what we saw was that in momentum space, PC gamma C plus M U of P and S was 0. In other words, the U's are solutions in momentum space of the Dirac equation. And the anti-spinors, the B's, do something similar. And I think that the B's, if I recall correctly, you just have a minus sign there, but I didn't write that down. So what this means is basically that P1A, U bar prime A, gamma A, U1, well, this is P slash on U1. P slash on U1 is minus I M U bar 1 prime gamma A U1. So in other words, this equation is saying that I P slash is minus M, and so P slash U, so I P, let me just write it down, minus I M. So P slash is minus, P slash U is minus I M. And then if you take the adjoint of this equation, what you get is U dagger of P, S doesn't matter here, minus I PC gamma C dagger plus M equals 0. So that's the adjoint of this, of the Dirac equation, momentum space. But on the other hand, remember, all right, here, I'm going to use this board, okay? Can you move the camera a little bit? What we would have would be U dagger of P and S minus I, let us say, PC gamma C dagger plus M, and now we multiply by gamma 0. And this is, again, another reason why this beta comes in. You see, the spatial gammas are Hermitian. Gamma 0 is anti-Hermitian. On the other hand, gamma 0 anti-commutes with the spatial gammas and commutes with the ordinary gamma. And so altogether, this is U dagger of P and S. Gamma 0 of I PC gamma C, and in fact, there's a typo here. PC gamma C plus M, and so this is then U bar of P and S I PC gamma C plus M equals 0. I slipped in an extra. All right, let me throw in an I. So I gamma 0 is beta, so there's the beta. And what happened here then is that for gamma 0 and gamma 0, we have that the gamma 0 goes through, but the gamma 0 flips the sign. For the spatial ones, the Hermitian conjugate doesn't flip the sign, but the gamma 0 going through flips the sign. So in all 4 cases, the sign flips, and you get that equation. And so what this says then is that, for example, P1A prime, U bar 1 prime, gamma AU1 is equal to minus I M U bar 1 prime gamma A U1. And so now if we subtract one of these from the other, what we get is QA U bar 1 prime gamma A U1, which is, let me just get this right. Q is P1 minus P1 prime, right? Yeah. So this is then 0 because this is minus IM minus IM U bar 1 prime gamma A U1. In fact, there isn't any gamma A left. Yeah, this was a mistake here. So let's see if there's another one over here. Yeah, this is a mistake. The gamma A is gone when you do this. It's basically P slash on U1 is minus IM U1. And so over here, there's no gamma A there. And so there's no gamma A there. There's no gamma A there. Which is just as well since there's no index here. And so this is equal to 0. And what that means then is that if we go back to, can you swing the camera around here just for a second? What we've got here is, in this case, this just changes gamma B into lower gamma A. That's what this eta does. But over here we've got these Q's. And the point is that the Q's on these just give us 0. And so consequently, the amplitude, after you use this equation, the amplitude is minus I E1 E2 over 4 pi squared Q squared 1 plus pi of Q squared delta fourth of P1 prime plus P2 prime minus P1 minus P2, and then U bar 1 prime gamma A U1 U bar prime 2 gamma A U2. Okay, so that's the formula after you've made use of these identities. Okay, and we should quit because we're over time.